You okay there? Hi, everyone who listens to us online. And we're starting, but
Hello, everyone. So today I'm going to present this paper, Explainable, Interpretable, and Trustworthy AI for an Intelligent Digital Twin System, a case study on remaining useful life. This paper was presented in Engineering Applications of Artificial Intelligence in 2024. So remaining useful life is a metric associated with critical components. For example, if we take example of an airplane has different components, and every component has a remaining useful life. And in order to do maintenance jobs, you need to know this metric. So this case study is on RUL. And a digital twin is basically a simulation of a physical system. And the rest of the three terms I'll explain in the coming slides. So in this paper, they have proposed a framework for an intelligent digital twin system. Intelligent because when you use machine learning algorithms, they call it intelligent digital twin. And then when we use machine learning, there is always this issue of trust arises, right? Because machine learning models, especially deep learning models, are a black box in nature. So it's important to find a way to explain the predictions of a model. So here comes XAI and IML, explainable artificial intelligence and interpretable machine learning, IML. So this paper justifies the role of XAI, IML for digital twin system for the prediction of remaining useful life, both locally and globally. So this organization, Prognostic and Health Management, PHM, use DTs to monitor and manage system health utilizing statistical algorithms and models. And DTs help in conducting condition-based maintenance, making maintenance decisions, and anticipate future failures in advance so that they could take actions accordingly. And XAI can help increase trust the RUL prediction of an intelligent DT system. And it could be any physical asset such as machinery or infrastructure or anything like that. So digital twin system, as I said earlier, it's a virtual representation of a physical system. It replicates a physical asset in the virtual environment, and it includes its functionality, features, and behavior, everything like that, right? And they just run a simulation, and then they know which system, which specific component would fail, and then they can take actions accordingly. So this DT's technology can reflect, mimic, and forecast the status of the operating physical system in real world, and is one of the best tools for a remaining useful life prediction.
Question. What does it remaining useful life mean?
So remaining useful life of a component, for example, if you take example of an airplane, like it has a propeller, right? And you want to know how long that propeller could last. So that metric is basically remaining useful life. For how long can you use a specific component before it fails, right?
So this is in the context of like.
Yeah, this is in the context of nuclear power generation.
Okay.
Yeah. So they incorporate AI ML in DTs. When you incorporate explainable AI in DTs, it can facilitate risk-informed decision-making related to RUL of a component and then streamlining high-performing simulations, right? So when you use machine learning, you should find a way to come up with some explanation so that the end user could trust could trust the model, right? So that's why we need explainable AI and IML. So the use of explainable, interpretable, and trustworthy AI is crucial for accurately predicting the remaining useful life in an intelligent DT system where they have used machine learning models. So basically, there are two terms like explainable and interpretable. The first thing, explainable AI, is used to describe an AI model, its expected impact and potential biases. So how can XAI be useful? It could be useful in building trust by explaining the rationale behind a decision, and it gives transparency, and then it can help with international regulations because those regulations oftentimes require to explain the decision-making process to keep it transparent. And then it improves user experience because user trusts the prediction if he knows what's exactly going on in order to make that particular prediction. And then it also helps in debug and improving the system. And you can increase the reliability and accuracy of the prediction using if you know the explanations or rationale behind a prediction. So here a bit difference between these three terms. Like explainability allows users to understand the factors most important in the model's prediction, whereas interpretability allows the model's prediction to be easily understood by non-technical users. So you have to make it easy for non-technical users in order to be able to understand the model's prediction. That is interpretability. And trustworthiness ensures that the model is not making predictions based on irrelevant or misleading features and is unbiased. Right. So intelligent digital twin framework, in this paper, they have proposed intelligent digital DT framework where they have embedded this XAI or IML component as well. So there are basically 5 major components in a DT. The first one is prediction module, system update module, data processing module, visualization module, and decision-making module. So the first 2 modules, system update and prediction module, require sophisticated ML algorithms. So this is the proposed framework. You can see on the right side that they have used a Bayesian filter for parameter estimations, and based on that they update digital twin system. And then they combine Bayesian filter with an ML algorithm for the prediction. And you can see at on the left side that they have used explainable AI and interpretable AI component in order to explain those predictions. So interpretable AI refers to the AI system's capacity to justify its judgment and predictions. So basically, explainable AI is an umbrella term within which you can say that interpretability comes, right? And it enables to comprehend the decision-making process for the user. So there are basically 2 strategies to go about it. The first thing is you can use transparent models. For example, we know that like decision trees, linear regression, and other linear models are transparent, right? They are intrinsically interpretable. We know what's going on there. So the first approach is use a transparent model. And the second explanation, thing is you can do post hoc explanations for complex models like deep learning neural networks, and where you don't know what's going on, right? So what you do is based on the input-output relationship, you try to come up with explanations. So there is post hoc explanations, which is about feature importance. So if you have a look at this diagram, the first set of classifiers or models are complex models like deep neural networks, gradient boosting machine, random forest, support vector machines. So these kind of models require post hoc approach to make it interpretable, to come up with explanations. And in the second set of models, which is a generalized additive model, decision tree, logistic regression, linear regression, they are intrinsically interpretable. So you can easily generate explanations with those models. So XAI means creating AI systems that can explain their actions. So like transparent models or post hoc explanations. And then interpretable AI refers to interpreting and comprehending a model's outcomes. Okay, so I've already explained this third point. We have different interpretable methods available in literature. They have used 4 such interpretable methods to conduct experiments. To name a few, for example, ReLU-DNN, explainable boosting machine, fast interpretable 3D tree sums, and partial dependence plot, explainable neural networks. All these are intrinsically interpretable models. And they haven't discussed
explainable neural network, it's intrinsically explainable. Is it like a certain architecture of neural network they're using, or what do they mean?
Come again?
When you say the explainable neural network is inherently interpretable, how so? Is it referring to a certain class of neural network?
Yeah, I think it's a certain thing, right?
Okay,
Because they did something to make it explainable, I guess, right?
There's a lot of
different
this.
paintings or something.
a ton of different ways that might shake down.
Yeah.
They say a ReLU-DNN is inherently explainable as well.
Yeah.
It's interesting. Disagree.
All right. So they use like 4 of these models, and the datasets used is PHM08. It's generated by CMAP simulation tool developed by NASA to mimic turbofan engine degradation under different operating conditions. So the first thing they have done is they've used different methods for feature selection. We do feature selection because it can reduce a large set of features into a manageable subset so that you could do the training process, and it can improve models' precision and interpretability, and it can remove redundant data instances. So the methods they have used are like 3 Pearson correlation, distance correlation, and feature importance. You can extend them one by one. Pearson correlation, it's a statistical technique to determine the linear relationship between 2 continuous variables. And it's computed for each feature with respect to target variable. And it's simple and straightforward method to implement, and it is most frequently used metric. But the thing is, it's not good with non-linear interactions in the data. Distance correlation quantifies the relationship between 2 variables and determines the most significant parameter for predicting the target variable. So the good thing about it is that it can reveal non-linear relationships between variables, but it's computationally demanding, of course. And then LGBM based feature importance, which is the third feature selection process. Light gradient boosting machine. It utilizes decision trees as its base model, and then it iteratively train multiple trees, and the algorithm assigns higher weights to observations that were poorly predicted in the previous trees, so that the focus could be given on that specific thing, and then it helps improve accuracy. And this feature importance method is capable of handling large data sets and missing values and categorical features. So these are the feature selection results. A, B, C. We discussed 3 methods, so these are the results. You can see features here like cycle, like the number of times the component was used is represented by cycle. And then different settings, setting 3, setting 11, setting 13, and stuff like how did that component being used under what settings, right? So these are the features here, and x-axis is basically RUI, remaining useful life. So you can see here from A, B, C that cycle has the most impact on the target variable, which is RUI. And it makes sense because if you use something more, then it's going to degrade faster, right? So that's one way to explain it. And they have also come up with multivariate correlation heat map. So we have features here, and we have target variable. If you have a look at the top right corner and top and bottom corner, you see that RUL and cycle has a very strong negative correlation, because when one increases, the other decreases, right? And similar trend we can see from the plot on the left side, which is cycle versus RUL. Okay, so for global explainability, they have used two methods, partial dependence plots and accumulated local effects. Partial dependent plots are an interpretability ML method to understand the relationship between a single feature and the target variable. And it's capable of finding linear or more complex relationships in the data, identify co-founding factors that might obscure the connection between an intriguing quality and the desired result. And it's easy to understand, so it works well for non-technical audiences. They can understand it easily, and it provides only partial picture if a feature is linked with other features. So there is a strong connection between different features. This method might not work as effectively as it should. And the other method is accumulated local effects. It plots the model's average prediction as a function of the feature of interest while maintaining the observed values of all other features. And it's capable to reveal linear and more complex relationship between features and target variables. And it relies on observed values. The previous plot relies on mean and median. So it relies on observed values to fix the values of other features. So hence it is less sensitive if you compare it with the previous plot. So these are the results with these two approaches. And this is the same plot, like it's cycle versus RUL. And they have conducted experiments with 4 different algorithms, interpretable machine learning algorithms, ReLU-DNN, EVM, fix, and tree. In some cases, the slope is higher, but the overall trend is same. Like if you increase the value of cycle, it decreases the value of RUL, which is remaining useful life. And then we talk about local explainability. So in global explainability, what we do is we talk about the behavior of model using multiple instances or all the instances, right? But in local explainability, you just use a single data point or a small set of data points to explain a prediction. So thus, hence we call it local explainability. One of the popular methods to come up with local explanations is LIME, local explainability model agnostic explanation. As it's evident from the name, it's model agnostic, and it provides local explanations for a single data point or a small set of data points. So this is just a toy example to understand the intuition behind line. So the black box, let's say the box model's complex decision function is represented by F. And here the background blue and pink background is represented by F. And the bold red cross is the instance being explained, right? And then line samples instances gets prediction using F. And it's based on size, right? Like size represents how far it is from the instance being explained. So that's the principle that Lime uses to come up with this dashed line, and then this dashed line is the learned explanation for Lime. So if you have a look, if you have a global look, you know that this is not the right prediction, but if you see it locally, the classification, the explanation is better. So these are the results with line for local explanation for a limited set of attributes, features. So it's a similar thing, right? Like if you have a look at the top rows in all 4 plots, cycle has the highest effect on RUL. The top 2 plots have more expressibility if you compare it with the bottom 2 plots, but the overall trend is same. That's it. It was a small paper. So if you have any questions, you can ask.
Yeah, can you go back to this slope plot, the one with Rilu, and then
This one.
no, like I don't see any plots, and like let me quote a person who all of us know, Vince Calhoun. If I don't see a plot of a brain, then the paper probably doesn't know what they're talking about. Where is the plot here of any detail? Like you were talking about a propeller or something. Like how does this look? Like what are we looking at here? Like
So the nuclear reactor is what they're.
Yeah, it was for a nuclear reactor.
yeah, but they're running it on some data, right? How does their data look?
I explained briefly the data set, but they haven't.
Like do they show the images of data or?
Yeah, they just showed these plots.
But what can I get from it? It's like on the x-axis is the predicted cycle of
Yeah.
failure. And on the y-axis is actual cycle of failure.
No, on the y-axis it's RUL, remaining useful life, right? And on x-axis it's cycle.
So what is that cycle? Is the predicted cycle when it will fail?
Yeah.
It's a normalized value too, right? Between 0 and 1.
So yeah.
So
Here's
this is predicted versus actual, then, right?
No, it's not. No,
This is an graph.
it's simulated. All of this is a simulation, right? But the plot is between cycle versus RUL, because that's what you want to look at, right? Like the usage of a component versus when it will fail.
So how does the model come into play? Usage of component versus?
This kind of look like they just learned a linear regression.
Yeah, I don't understand, yeah, exactly.
In the decision trees are not linear, I guess, but. Yeah.
It's definitely linear. It's linear view.
Kind of, yeah. Well, my question about these kinds of systems is that I've seen this discussed on a few different forums. It's like, we have ways of simulating physical systems that are pretty reliable and are based on like systems of differential equations, simulating individual components. Why do we build, like just throw ML models of data that are black boxes for this kind of prediction? You have to add all this extra explainability stuff onto them. We have simulations that work just as well, or like often quite better because they have less uncertainty about them, and they're they are inherently transparent. In this paper, they don't compare with any like just standard simulations. Like yeah, so that's why do this? why add AI if it's not like if we have ways of simulating things, that are built on the knowledge of the system, it's kind of a polemical question,
I don't
but
know about this paper, but I know that like DeepMind had a paper about a nuclear fusion reactor where was too chaotic to predict it with anything, so they did it with DeepMind.
right, so that makes more sense. If it's the kind of system where a system of equations could never describe what the system is doing, or it's chaotic in some way that. I mean, you could build a chaotic system of equations, but yeah, or if it's like difficult to learn, that makes sense, but they don't, because they don't talk about that, or it's not mentioned, I'm not seeing. I'm not seeing it, and if this is the kind of relationship we could predict with these models, I don't know, it doesn't look that. I mean, it's linear, right? What's the point?
Yeah, it's kind of obviously linear. But about reactors, just to correct, so in the 60s when they started building them, they had built differential equation. I forgot exactly what years that's maybe the tokamak thing, but they had differential equations that describe the system. They just were too long to compute in time to make a decision to change the magnetic field and stuff. And back then, they trained the neural network in the 60s or like around, or maybe that was 70s. They already trained the neural network on the output of those equations. And the point was not the accuracy as much, but the speed of reactions. So it predicts quicker than you will compute. But offline, when you're training network, you don't care. Right. So you wait longer and you get a lot of training data that way. And now they kind of, as most 90% of deep learning is reproduce the results of that time with modern hardware and of course improved and blah, blah, blah. But they've already done that. Like the novelty is not there. Our predecessors stole all the novelty, so we have to rebrand.
Yeah.
And call it. Yeah, but this paper is strange, didn't you find? I mean, it's my interpretation. I was like waiting and waiting for Baker's explanations. Yeah. Why would you trust any of those models? Like they want to trust and say there was a question or a statement there in the beginning of your slides that by law you're required to have an explanation of the failure or something.
Yeah.
So how does that help us? So imagine a lawyer who doesn't know anything about even a linear model. Yeah. So what would they get from?
I know from this, I think maybe we could know the number of cycles. We can use a specific component. And that could be helpful, right?
No, but as an explanation, what is explanation here? This is a model making a prediction. Where is the explanation?
Oh, it's these like 2 or 3 different post hoc methods that they use, right? Yeah, that's. Yeah,
I don't know.
sure, you could do that. Just I don't know if I buy that like a lawyer would understand even the difference plots or whatever they were called. I think there's a big gap in what people count as explainable AI and what regulators actually want to look at for these kinds of systems. It's usually important.
Yeah. Like I don't see it from here. Maybe it's in the paper, but I don't know. Anyone else? Questions, comments, concerns, praise for the work? So those are explanations.
Yeah, these are local explanations.
By local explanations, you mean saliency?
Kind of,
Yeah.
Or coefficients in linear regression, for example.
I were a regulator, I don't think I would approve this system, that's my. Oh, that's such a weird laugh.
I wonder if we can use these models that you just explained in neuroimaging too. I mean, using fMRI images or MRI images as the input to the models.
Yeah, I think we can, I mean, so I have used, not Lime, but, something similar to that, right? To generate saliency maps and then come up with try to come up with global explanations. It didn't work well, but I mean, you can, of course. You can use, saliency maps as features, and then you can come up with some global explanations.
Did you get the linear relationship?
No, I
Okay.
So I was trying to come up with like, so I have a lot of, we have a lot of instances, right, data points, right? So I wanted to come up with representative data points that extends it globally, something like that. That's what I was trying to do.
I think something like that would work for this kind of system too, like what, so if you have a time course of like a sensor on the system or something, like, pick a segment of the sensor readout that indicates that, the life expectancy of this component is, very low now. Like that would make sense, and someone, an engineer could be like, oh, this component, I'm gonna, stop the works or whatever, take a look at this component, oh yeah, it's worn down, like that makes sense if you could like, identify things, in that kind of way. I didn't really see that in here too much. If this is like, so they call it a case study, do they like talk about specific regulations and regulators that looked at this and how their response to it was, or is it just like an application and they're calling it a case study? Okay. Yeah. I would like to see more like actual AI case studies where you have like lawyers looking at this stuff and politicians looking at this stuff, because other people who don't get it, and we need them to get it, at least enough to, understand what they're regulating. And now you just have people who see ChatGPT and want to apply blanket rules to all models based on what ChatGPT does, because they don't know what's going on in these systems otherwise.
What do you mean, apply blanket rules based on what ChatGPT does?
I mean, look at the popular response to AI that's coming out right now. The regulations that are being talked about are all in response to large language models and some diffusion models as well, and some copyright law that might be questioned because of what they do. But
Well,
rules that are going to come out, I think, are going to be more broad reaching than they ought to be, because they're responding to systems that they don't understand.
so we can look into history. What happened when things like Netflix, well, first Napster, and then Netflix and streaming platforms came out and killed all of the businesses that were renting out. It's kind of the same with copyright. It's
There was a national security issues though at stake, which is what people are worried about.
with generative model.
Bot farms, they're worried about intellectual properties, the hot topic right now with the diffusion models and DALL-E and all that.
Yeah, but the same with Netflix, intellectual
yeah.
property, like anything, any streaming platform, any online kind of stuff, instead of like having a single copy right here.
Oh, right.
That's what we had, we solved the problem. By licensing, I guess, micro licensing, when you put your song on YouTube Music, you get a little bit share every time somebody listens to it, stuff like that, so maybe.
So as an artist, I would own 1/3 of the golden ratio in my art. How would that work then? I'm just curious how that could be applied.
Well, I have different opinions on the subject, because you don't pay license fees to all of the stuff that you looked in your life, and that made you draw that because it's still a creative combination, but it's a combination. It's not new. I mean, there was a guy in Bible who said that, right? Nothing is. I mean, it was known for quite a while, at least 3,000 years. So then, open source. Radical. Nothing belongs to you anyway. I mean, yeah, whatever you can sell, that's fine. But then,
The issue is that OpenAI was making money off of stuff that they were using that was not taken with permission.
yeah, that's a different issue, but,
Well, that's probably why they're not launching Sora. They're trained on YouTube.
The
yeah.
videos for that are crazy. For that model.
It's not real.
Like, people would enjoy, I mean, we're kind of diverging from this paper, maybe I should stop the recording, thanks, and look at.
Yeah, you're welcome.
Yeah, thanks everyone, online, who.
I think for showing them are sort of
Join us.
interesting.
Yeah, and thanks, Zafar. Next topic is, as far as I know, is on quantum computing, I have no idea what that.